and welcome to the Focus Training Group's short video on calculating ZS. What values do we need to calculate ZS? ZS equals ZE plus R1 plus R2. This is the equation we will be using to calculate our ZS. The importance of verifying our ZS at the design stage is to ensure we will have our required disconnection times before the circuit is installed. So let's have a look at some of those components of that equation. ZE. ZE is the external earth fault loop impedance of the supplier's line and earthing conductors measured in ohms. This value cannot be calculated by the designer. It can be found by inquiry or by testing. If you do not know the ZE, it is always recommended to use the maximum value for that particular type of earthing system. Section I of the IT on-site guide will give you these values. Our R1 or R2 value. R1 is the resistance of the line conductor, measured in ohms. R2 is the resistance of the circuit protective conductor, measured in ohms. R1, R2 is the combination of these two values. As long as you know the length of the circuit and the cross-sectional area of the conductors, this value can be calculated. Appendix I of the on-site guide is a good place to help you with these calculations. Table I1 gives us values of resistance per meter for copper and aluminium conductors. This table can be used to help calculate our R1 and R2 value. Let's take, for example, a 2.5 line conductor with a 2.5 CPC. We can see that the resistance of 1 meter of this size conductor will have a value of 14.82 milliohms worth of resistance. 1 meter of a 2.5 line conductor with a 2.5 CPC will have an R1 R2 value of 14.82 milliohms. Because this value only represents 1 meter of the circuit, we will have to multiply it by the length of the circuit to get the full value of the R1 R2. Also, one other consideration is the fact that the resistance calculated will be the resistance of the circuit when it is dead. To take into account that the circuit will be carrying current and subsequently be warmer, a rating factor has to be taken into account. These factors can be found on table I3 of the on-site guide. This table shows the multipliers to be used for different types of cables in different types of installation methods. For example, a 70° C thermoplastic multi-core cable where conductors are bunched together would have a multiplier of 1.2 applied to the milliohms per meter value. So let's have a look at using some of those values. We have an example here. An installation has a ZE of 0.25 ohms. We are wiring a lighting circuit to supply a piece of fixed equipment. This circuit is 24 meters long and is to be wired in a 4mm line conductor with a 4mm CPC in 70° thermoplastic cable. The protective device is to be a BSEN 6098 32 amp Type B MCB. So let's calculate the ZS for this circuit. We have our equation ZS equals ZE plus R1 plus R2. The first part of the equation is easy enough to find. It is the ZE, and we are told that ZE is 0.25. It informs us that in the actual question. Next, we have to go about calculating the R1, R2 value. And we get that value by multiplying the milliohms per meter value by the length and multiplying it by the temperature factor. We also divide the value by 1,000 because the answer we get will be in milliohms. If we divide it by 1,000, it'll bring us up into ohms for us, which is a much more usable value. So firstly, I need my milliohms per meter value. For a 4mm line conductor with a 4mm CPC, we can see in the table that we have 9.22 milliohms per meter. So we've got 9.22 milliohms worth of resistance in 1 meter for a 4mm line conductor with a 4mm CPC. Putting that into our R1, R2 equation, we have 9.22, that's our milliohms per meter value. We have a 24 meter long circuit, and we also have to find our temperature factor. Using table I3, we can see that it's 1.2, which at the bottom leaves us with R1 plus R2 equals 9.22 multiplied by 24 multiplied by 1.2 over 1,000 will give us an R1, R2 value of 0.26 ohms. That would be the resistance of the entire length of that circuit. Once we've got all those values, we can put them together to get our overall ZS. So ZS equals 0.25, which was our ZE, plus our R1, R2 values, which we calculated to be 0.26. So overall, ZS equals 0.51 ohms. The overall ZS of that circuit would be 0.51 ohms. Now we've got that value, we also have to make sure that our ZS would be low enough to give us a sufficient disconnection time. We can do this by checking the maximum permitted value from BS7671. Yeah? And we can see, looking at table 41.3, that 60898 type B 32 amp MCB has a maximum permissible ZS of 1.37 ohms. Our calculated value of 0.51 is well below that, so our disconnection time of 0.4 seconds would be achieved. You do have to be careful when referring to your BS7671 when checking your maximum ZS values, especially for fuses. They have two tables, one table to represent a 0.4 second disconnection time and one table to represent a 5 second disconnection time. Do make sure you're referring to the correct table. Thank you very much for listening to our short presentation on calculating ZS.